Hello differential equation students. In this video we'll talk about how do we solve higher order linear differential equations with non-constant coefficients. In previous videos we looked at how to solve higher order linear differential equations with constant coefficients. Now we're going to take a look at the non-constant coefficients. So the method that we're going to use in this one is what we call the reduction of order. By the way, as per your book section, this is section 4.2. But I'm going to call it as section 4.3, but as per your book it's section 4.2. So let me give you an example of what do I mean by higher order linear differential equations with non-constant coefficients. If you take a look at the second order, the way it's going to look like is the following. You're going to have a1 of x y double prime plus a2 of x times the y prime plus a sub 0 of x times y is equal to some sort of let's just say g of x. If you take a look at this one, as you see here, this is a function, not a constant anymore. This is a function, not a constant anymore. This is a function, not a constant anymore. So this is a second order linear differential equations with non-constant coefficients. So if you want to take a look at some example, here's an example or one right here. X squared plus 1 times the y double prime minus 2xy prime plus 2y equals 0. Again, this is a homogeneous problem, and here you have a non-homogeneous problem where the coefficients are non-constants. This is a constant coefficient, but this one is non-constant coefficient. So this is an example of a second order linear differential equations with non-constant coefficients. By the way, there's a nice formula just like similar to your integrating factor method in the first order linear differential equations for this as well. Suppose if you can rewrite this differential equation, right? This differential equation, just so you have a homogeneous problem, let's just say you have a homogeneous case where then this is g of x is equal to 0, then we're looking at this right here, something like that. We are looking at something like this, right? Equal to 0. If you can rewrite this, differential equation in this form, something like this, y double prime plus p of x times y prime plus q of x y. Basically, you're dividing the entire thing by this one. Then what you can do is you can find the y2. So suppose y1 is a solution to this one, and you can find the y2 using this integral, similar to your first order linear differential equations. So again, you find the p, integrate that, integrate it with respect to x, and then raise it to the e to the negative integral of p of dx divided by y1 squared, and you integrate that again and so on. You can do that. Since it's a formula, I know you can do that, but what I'm going to go through, I'm going to give you a process how this works, and that process is not only helpful for solving the homogeneous one, that also is helpful for solving the non-homogeneous case as well. So let me go through the process and let me show you a very simple example, and then we will move on. So what is that process? The process is very simple. Step number one is you want to make sure that number one, for a homogeneous case, right? The step number one is, remember, for a homogeneous case, right? So you're talking about higher or second order. Let's just take a look at the second order example. Second order linear differential equations. That means that we are looking at something like this. I think I should call this is a a2 and this is a a1. I should call this the a2 and this is a1. So you have something like this, a2 a function, right? Y double prime plus a1 as a function times y prime plus a sub 0 of x times the y is equal to 0. We're looking at the homogeneous case, right? This is going to have two solutions. This is going to have two solutions, and we call it as a fundamental set, and that is going to be y1 and y2, right? And the general solution is, right, then we know that we can write the general solution, and the way we write the general solution is we are going to say y is equal to c1 y1 plus c2 y2. So now what is given to us? What is going to be given to us is someone is going to give us one of them. Let's call that as the y1. And we're going to figure out using that y1 how to find the y2 is the question, right? So that's what this is going to be. Suppose someone gives you y1. How do you figure out the other one? Because this is going to have, since it's a second order, this is going to have two linearly independent solution as our fundamental set of solutions. So let's see how do we do that. So the very first thing that you want to do is we're going to use some sort of substitution. We're going to use some sort of a substitution method in here. And the substitution is the following. We're going to say, we're going to assume, right? We're going to assume that y2, we're hoping that y2, what if that y2 happens to be a function multiple of y1? Right, for the simplicity, I'm going to write v times y1 for the future purposes. But here note that the v is not a constant, rather v is a function, right? Then what do? Then we expect this y2 to be a solution. Then what we are going to do, we are going to plug this y2, this vy1 into your differential equation right there, right? And then then what's going to happen is you're going to have a transformed differential equations, right? So you're going to have the step 3. You're going to have some sort of, once you do this, right, once you plug it in, you're going to have a transformed differential equation that's going to involve, so you're going to have a differential equation that's going to involve v and y1, right? A differential equation of that. Then what do? You're going to, that's going to be a second order. Then you're going to transform this back again, and that's what the reduction process is. You're going to say that w, you're going to see that when I do an example, this I'm going to call w as my v prime. Then what's going to happen is that the w prime would be v double prime, right? Then this differential equation, will be reduced. This is the second order, right? This is the second order, will then become reduced to a first order differential equation. You all know how to solve the first order differential equation, but this is going to be first order differential equation in terms of v, right? It's going to be first order differential equation in terms of v. And by the way, this y1, we know the function, right? That's going to go away. It's not really going to be there in the equation, because y1 is going to be given to you as a function, right? So this is technically a second order with respect to v. And then we're going to transform that into a first order with respect to your w, not v, by the way, a w. You know how to solve the for w. The next step is to solve for w, right? Then once you solve for w, then the next step what you're going to do is you're going to say, well, now you know your next step is to figure out your v. You know the v prime is equal to w, so therefore your v is going to be integral of w dx. Then the next step is we are going to say our y2 is equal to v times the y1, and then the next step is you write down the solution as y is equal to c1 y1 plus c2 y2. As simple as that, right? As simple as that. And that's how we would solve. That's a process, right? That's a process that we're going to follow. Let me show you an example how does this process going to work. But that is a general process in solving this homogeneous case. And this is the same idea. The same idea is going to work for the non-homogeneous case as well. So let me try to execute the plan over here. So to do that, what I'm going to do is let me just shrink this a bit. So let me just rearrange it. I just rearranged it. Let's take a look at how to solve this particular problem right here, right? Let's take a look at this particular problem right here using the methods that are processes that are described in this, right? Let's see how do we do that. So the step 1, as I said, first I'm going to, oh, by the way, the first solution is given to us. In this case, the first solution is y1 is equal to x. So we need to find the y2. So what we have is, we know the differential equation is given to us. The first solution is given to us. So you need to figure out the y2. So the step 1 is already taken care. So let's take a look at that. Let's write it down. The first solution is y is equal to x, right? The second step, as you see, I'm going to assume that y2 is a function multiple of the y1, which in this case would be simply v times x. Then what I am going to do, now I know that y2 is a solution to the differential equation, right? So I'm going to plug it back in. To do that, I need to find the y2 double prime and y2 prime and so on, so that I can plug it back in. So let me quickly do that. y2 is equal to that, so therefore that is going to tell me my y2 prime. If I use a product rule in here, ladies and gentlemen, I would have a v prime times x plus v times x prime, which is 1, and my y2 double prime would be v double prime x plus v prime x, v double prime x plus v prime, not v prime x by the way, plus v prime, and plus another v prime, right? That second v prime comes off of this, the first one comes off of this, right? Now if I simplify this, ladies and gentlemen, you would agree that I'm going to have v double prime x plus 2 v prime. The next step, what I'm going to take all this information, y2 prime and y2 double prime, I'm going to plug it back into this differential equation and then see what happens. When I do that, as you see, as my third step, let me plug it back in. If I plug it back in, I'm going to have x squared times y2 double prime, so that would be v double prime x plus 2 v prime plus minus 4 times x times the y2 prime, which is v prime x plus v, plus 4 times y, which is v times x, and that is supposed to be equal to 0. Now if I really pay attention to this, now I'm going to simplify this, as you're going to see me 4xv plus and 4xv, that's a plus and this is the minus, right? So this is going to get cancelled. Is there anything else I can cancel? I don't think so. Maybe I can simplify v primes and v primes in here, but I don't think there is anything I can cancel. So let's simplify that what I have. If I simplify this, let me simplify the v double prime. So I am going to have x cubed v double prime plus 2 x squared v prime minus 4 x squared v prime is equal to 0. If I simplify this, that's going to give me x cubed minus 2 x squared, v double prime, x squared v prime is equal to 0. If I pull out the x squared, I am going to have x v double prime minus 2 v prime is equal to 0. Again, I already assumed that x is positive. Since I assume that x is positive in here, right, I can divide by the x squared. If I divide this by x squared, ladies and gentlemen, I am going to have a differential equation that is if I divide by x squared, that's going to give me x v double prime minus 2 v prime is equal to 0. And if I simplify this, it's going to be v double prime minus 2 over x v prime is equal to 0. Still, by the way, I can do this because it's x is positive, right? Otherwise I won't be able to do it. All right, so now what I'm going to do in the next step, ladies and gentlemen, so where we are right here. Now we have a second order differential equation in terms of v. So I'm going to use this substitution. I'm going to use that to reduce into a first order. Let me do that. If I do that, let me do the substitution step. Let me use a different color. I'm going to say w is equal to v prime, and so therefore the w prime would be v double prime. If I do that, then this would become w prime minus 2 over x times the w is equal to 0. As you see, this is a first order linear differential equations. Again, I can use the integrating factor, or I can use the variable subproblem method. If I use the variable subproblem method, I can rewrite this as dw over w is equal to integral it's equals to 2 over x dx. And if you do the integration on both sides, you're going to see ln of w equals, ln of x squared. You don't have to worry about the constants, so this because it's going to be taken care anyway. So if I simplify this, it's going to give me my w to be x squared, right? My w is going to be x squared, and if I take the natural logarithms on, if I take the exponential functions on both sides, now that means what? I got my, so we are right here, ladies and gentlemen. So we solve for w. We solve for w. As you see the next step, right? That's what we have. This is our step number 4. This is our step number 4. As now the next step is to figure out the v. So let's do that. If I try to do the v, then you know that v w is equal to v prime, which is equal to x squared. That tells you that v is equal to x cubed over 3. It's basically the integral of x squared dx, as you see that. And we are done almost. So the next step, as you see, the step number 6 is to figure out the y2. Now we have the so we're going to use this step. Now we have the v and we have the y1. We can figure out the y2. If I do that, then this next step, that's going to give me my y2, which is what do you see here, or what you're going to see here is y2 is going to be v, which is x. Let me write down so that you can follow along. y1 times v, which would be v is x cubed over 3, and y1 is simply x, so that's going to give you x to the 4 over 3. And again, this constant doesn't matter, so therefore, you know, your fundamental set of solution is going to be y1 and y2. y1 is x and your y2 is x to the 4 over 3, and that's what we use reduction of order, right? Use reduction of order method. So therefore the general solution is y is equal to c1x plus c2 x to the 4 over 3. As a matter of fact, I really don't have to say, you know, x to the over 3. I can call this as a, you know, c2 bar, and I can say this is c1x plus c2 x to the 4, and where c2 is equal to c2 bar over 3. If you want to say it, I can say it, but it really doesn't matter, so you can just leave it like that, because these are arbitrary constants. It's not a big deal. But if you're working, if the initial condition is given to you, then you have to be a little bit careful in here in figuring out, you know, c1 and c2. At the time you may want to keep the 3, but if you don't have an initial condition, we are looking at, you know, arbitrary constants being multiplied, so we're gonna have to worry about it again because of this reason. By the way, the arbitrary constants, right? That's why we're gonna have to worry about plus ln of c, or, you know, plus ln of c in here. We don't have to worry about the plus c in here or plus ln of c in here, because of that reason, because we know that that's going to be eventually taken care somewhere over here. And that's the same reason, by the way, here also we will not have another c here. The same reason, because it will be taken care eventually anyway. And that's how we solve the homogeneous case of higher order, in this case second order, linear differential equations with non-constant coefficients using the reduction of order method. Again, we say it's reduction of order method. That's because this method helped us going from second order into a first order. That's your reduction of order process right there. Now let me show you how do you solve this in a non-homogeneous case. Non-homogeneous case is also very similar. The process wise it's exactly the same, except that we need to be a little bit more careful in how do we define the functions and so on. As you know, in a non-homogeneous case, we are going to have, as you know, the solutions, right? The solution, general solution, is going to have two components, right? The general solution is y is equal to yc plus yp. Here, by the way, again, we are looking at, what are we looking at? We are looking at this kind of differential equation, right? This kind of a differential equation. What do I mean by this kind? So we are looking at non-homogeneous case, right? So we have a g of x right there. These are non-constants, ladies and gentlemen. These are non-constants, right? That's a function there. So you're going to have a YC and a YP. So you find the YC. So here again, to someone, I think we expect, if the problem is not easy, we expect someone to give you the Y1, right? Let's just say someone gives you the Y1 of X. Then what you can do the Y2 by the same process we did earlier. So to find the YC, YC is going to be a linear combination of, Y1 and Y2, right? So using Y1, you can figure out the Y2 the same way we did earlier. Then how do you find the YP? To find the YP, what do you do? Here also we're going to do the very similar thing. Here I'm going to say, so remember here we said Y2, we would set Y2 to be a function multiple of Y1, correct? Similarly, we're going to say YP is also a function multiple of one of them. Yeah, now that you have your Y1 and Y2, right? Now that you have your Y1 and Y2, because from the Y1 you're able to find the Y2, right? Now to find the YP, what are we going to do is we are going to say this is also U times Y1 or Y2. You can say Y1 or you can say U times Y2. Either one is okay. But the difference is the following. Remember, this Y2 is a solution to a homogeneous problem. So therefore, when you're going to plug in, you're going to plug this into this differential equation, which is A2 of X, Y double prime plus A1 of X, Y prime plus A sub 0 of X, Y equals to 0, because that Y2 is a solution to the homogeneous problem. But the YP is a solution to the non-homogeneous problem. So what you're going to do now here, what you're going to do is you're going to plug in not to the 0 case, but you're going to plug this into the non-zero case. Here you're going to plug this into a non-zero case, and of course then that means that it might become a little bit more involved in terms of solving. We're going to see a problem, right, in solving and so on. And so that's a one way to do. I mean, that's a process. That's not the one way to do. That's how the process works. Sometimes, by the way, we might be able to figure out Y1 and Y2. For example, if a problem is given to you something like this, let's just say, let's just say we need to solve this problem. Solve Y double prime plus Y is equal to secant X, right? And nothing is given to you in this case. No, Y1 is not given, Y2 is not given. Then what you can do is, this is a second order in this case, second order linear differential equation with constant coefficients. So we can use the characteristic equation, what I call M&M methods, to find the Y1 and Y2. Right? You can find the Y1 and Y2 using that way. And then to find the YP, what you can do is you can use any of the Y1 and Y2s to do that. I'll show you this example in a moment, but I just want to quickly say how does the process work. If the problem, if the problem is something like this, let's take a look at, for example, something like this, right? If a problem is something like this, then we don't have a choice, right? Someone has to give you your Y1, then you find the Y2, and then you find the YP, right? But if a problem is given to you something like this, there is a much easier way to do that, to find the Y1 and Y2. But you cannot find the YP in this case from the previous methods, annihilator or superposition. The reason because there are no annihilators. You can't find annihilator for secant X, because secant X is not sin X, right? You can't find the annihilator for this one. For that reason, you cannot use the previous method. You have to resort to some other methods, and again, the reduction of order is the method to do. So let me quickly do this on how to find the YP in this case, but the same process should work for everything else. So let's see how do we solve this particular problem. So again, as I said earlier, the general solution is Y is equal to YC plus YP, right? And the step one is let's figure out the YC, right? Let's figure out the YC, which is a solution to the homogeneous problem. In this case, it's very simple. That is Y double prime plus Y is equal to 0. You all know how to solve them. The characteristic equation here is, m squared plus 1 equal to 0. And so therefore, m is equal to plus or minus 1. Is that right? I'll give you 3 seconds. No, it's not right. That's wrong. It should be plus or minus I. And so therefore your fundamental set of solution for the homogeneous case is going to be cosine x and sine x. So you got your y1 and y2. That's your y1 and y2 right there, right? Now let's see how do we find the yp. And so therefore, by the way, let me rewrite while I'm here. Let me write down the yc. Yc is going to be c1 times cosine x plus c2 times sine x, right? Now how do you find the yp? That's our step 2, right? How do you find the yp? To find the yp, as I said earlier, what I'm going to do, I'm going to use here I'm going to use reduction of order. I'm going to use reduction of order. So how do you do that? So here was, as I said earlier, what I'm going to do is I'm going to assume that yp is either uy1 or uy2. So what is the best way to do? There is really nothing. There sometimes it's not really the best way or best way or worst way. There is nothing like that. So here what I am going to do is, I'm going to, since secant x, sometimes it helps, since secant x is 1 over cosine x, so I feel maybe it's better to choose your yp as a function multiple of cosine x. Your yp as a function multiple of cosine x. I'm hoping, sometimes some things might get cancelled, so it will be the cosine and cosine. It may not happen. We don't know. But in this case I know, but in generally we don't know. It may not happen. So therefore in this case the better option would be choosing your yp as a function multiple of cosine x. Again, ladies and gentlemen, there is nothing that stops you to try. If you want to try it, you can say this is v times sine x, right? That's perfectly okay as well. For example, if this happens to be a tan x, right, then it might, you might choose sine x, and that might work very well. We don't know, right? So I'm going to go with that. Now what is the next step? What I'm going to do, I am going to plug this back into my original differential equation. And what is the original differential equation? The one with the non-homogeneous one, right? The one with the non-homogeneous one. So I'm going to plug this back into this differential equation. To do that, I should know my second derivative, I should know my first derivative, I should know the function. I know the function already. I'm going to find the first derivative, and I'm going to find the second derivative in a moment. So let me quickly do that. If I do that, then you agree with me that my yp prime is going to be, if you choose my y2 to be this one, I'm not choosing that. If you want to try, you can try it on your own. So my yp prime, just for fun, try it out, right? Yp prime is going to be a v prime times the cosine x using a product rule plus v times negative sine x, as you see that. So if I simplify this, you would agree with me, in the interest of space, I'm going to say this is, minus v sine x, minus v sine x. And what is the yp double prime? Yp double prime is going to be v double prime cosine x minus v prime sine x minus v prime sine x minus v cosine x, right? So if I simplify, this is going to be v double prime cosine x minus 2 v prime sine x minus v cosine x, right? That's my yp double prime. Now what is the next step? The next step, what I'm going to do, I'm going to plug this back into my differential equation, and then I'm going to solve it and see what's going to happen. So what is the differential equation that I'm working with? The differential equation that I'm working with is y double prime plus y, right? That's the original differential equation, right? Because that's the differential equation. That's what we're looking at here, right? This is the non-homogeneous case. In this case, that's our non-homogeneous case, right? So I'm going to plug it back in here. If you plug it back in here, ladies and gentlemen, I have y double prime plus y is equal to 1 over secant x, right? That's what I'm going to plug it in. That's very, very important, right? So 1 over secant x, which is 1 over cosine x. All right. So now let's see, how do we do that? If I plug it in, what do I get? Second derivative is, I'm going to use a second derivative in here. Which is going to be v double prime cosine x minus 2v prime sine x minus v cosine x plus y, which is v cosine x v cosine x is supposed to be equal to 1 over cosine x. And as you see here, this v cosine x and this v cosine x gets cancelled because they are of the opposite sign. And I am going to be left with, what do I have here? v double prime minus 2v prime sine x. This is a cosine x v double prime cosine x minus 2v prime sine x equals 1 over cosine x, right? That is what I need to solve for. All right, so now it's a second order differential equations in terms of, it's a second order differential equation in terms of, v. So therefore, next step, what we're going to do the reduction step, right? That's our next step. We know how to do the reduction step. The reduction step is we're going to say w is equal to v prime. The w prime is going to be v double prime. If I do that, then I am going to have w prime cosine x minus 2w sine x is equal to 1 over cosine x. Let me divide the whole thing by cosine x. Then I'm going to have a w prime minus 2 sine x over cosine x. W is equal to 1 over cosine squared x. That is what I have, right? Now, you can find the integrating factor and you can work it out and so on. It's a first order linear differential equation that are non-homogeneous type. I think that's related to the worksheet number 2. Worksheet number 2. So right after the variable separable, you can do that. If we do that, what do we get? Let me quickly do that. If you do that, ladies and gentlemen, we are going to have so in this case our p of x, p of x equals negative sine x over cosine x, right? And so therefore the integrating factor is going to be e to the minus 2 integral of sine x over cosine x dx, right? And if you do that, that is going to be, the derivative of this is this with a negative, right? Negative is right here. So that is going to give you e to the 2 times ln of cosine x, which is going to be e to the ln of cosine squared x, which is going to be cosine squared x, right? So your integrating factor is that. So therefore the solution is the w, that w is equal to 1 over cosine squared x, or let me write it down the way we did earlier, going back to what we had before. W times the cosine squared x is equal to, as you know, integral of cosine squared x times, if you take a look at this, I have a cosine, that's a q, right? Here's our q. The q is 1 over cosine squared x, so I'm going to multiply that by q, 1 over cosine squared x. This is the integrating factor. This is the integrating factor. This is your q of x, right? And dx. And the good news is, see, the reason that I chose that one, just look at what happened. This cosine squared x and this cosine squared x they go away. So that tells me my w is going to be simply x. That's going to be simply x. So therefore, w cosine squared x is going to be x. So therefore, my w would be x times x over cosine squared x, which is x times secant squared x, because the secant is the 1 over cosine. All right, so I got my w. Now we still need to figure out the v, right? Or in this case, I call it as a v, right? So now the next step is to figure out the v. v which is equal to we know that integral of w dx, which is the integral of x secant squared x dx. You can do the integration by parts. I'll let you do that. If you do that, again, this is not easy. It's a lengthy process. In the interest of time, I'm going to just give you the answer. If you do the integration, the solution to this integration is going to be x tan x plus ln of absolute value of cosine x, right? That'll be the integration for this. Again, it's a lengthy process. I'll let you do that. And so therefore, ladies and gentlemen, the next step, right? What is the step number? So we did the reduction of order, we solved it. So this number is step number 4. Next step, you want to call this step number 5. The next step is step number 6, which is to write down the in this case not y2, yp, which would be a v times the y1, which is v is this. So let me copy paste it. And then multiplied by y1, which is, I have a space there, times cosine x, right? Times cosine x. And by the way, I can really simplify this because tan x times the cosine x is sine x. So if you simplify this, it's going to be x times sine x plus cosine x times ln of absolute value of cosine x. That's my yp. And so therefore, the general solution, which is y is equal to yc plus yp, which in this case would be c1 cosine x plus c2 sine x. That's your yc, and your yp would be x sine x plus cosine x times the ln of absolute value of cosine x, and that's your yp, and that is your solution y. And that's how you solve this differential equation using this non-homogeneous second order linear differential equations. In this case, this one has a constant coefficients, but even if it's not a constant coefficients, that's how we work it out, and that's how we solve using the reduction of order. And here's the problem. Try it on your own. This is it's a nice problem. Try it on your own and see what you get. Again, this is a homogeneous case, so it should be relatively easier for you to work it out. All right, let's stop it right here. In the next video, we'll take a look at how to solve problems of similar type using there's an easier method of finding the yp's. This method only works for finding yp's, but how to use the variation of parameter, or also known as Wronskians, to figure out the yp's. All right, I'll see you in the next video.